Great. Thanks for the introduction. We will talk about how we can gain any understanding about what these deeper models are actually doing. And this is like a joint work with like a village of people by now somehow. For deep learning, you always need somehow a lot of people to get these things to work out. I will kind of mention them along the way. I'm also like a participant in the long program. And there, of course, we are tackling kind of very kind of diverse questions of intelligence. And this week, we're focusing on kind of like deep learning perspectives. And what we've kind of discussed already this week in the talk so far is like perspectives of robustness and generalization, kind of scaling laws and optimization procedures, information theoretic perspectives, and a few more. I will not go into this direction. In my talk, I'll kind of focus on the case where we already can assume that we have some system that's capable of some intelligent task solving. But since these models are so complex, we have difficulties actually understanding what's going on inside of them. So one of the key questions is how can we gain insight into the kind of features that the model has actually learned and the mechanism that it implements. I think in this context, often like this idea of a black box comes up. So I wanted to say a few words on that. So yes, to some extent, like these deep architectures are black boxes because we don't understand them, but it's still a very different scenario to, like, let's say, investigating the human brain, because there we don't have full access to all activations and all weights and full transparency. So the notion of a black box is kind of like maybe not the perfect analogy for like neural networks, but yeah, it's just like has been heavily used. Still it's very difficult, even with having access to all internal weights and activations, to make sense out of it because they are so deep and so highly complex. That's just as a small intro here. So the typical class of problems that we are looking at in explainable AI looks mostly something like this. So we have some input image X, which here is kind of a histopathology slide, and we give it into our trained classifier, and it can correctly predict that it is like a cancer cell. But for any expert or anyone that's interested in deep learning, this is kind of frustrating because we actually have no idea why this is the case. So the field of explainable AI tries to resolve this problem by kind of propagating back through these networks and giving you these type of heat map type of attributions that tell you why a certain system made this decision. And this field of explainable AI is kind of quite big by now, so it kind of grew pretty much in parallel to deep learning as a field. And it came up with really like a zoo of different methods, how you can kind of achieve these type of heat maps. And maybe like a few words on why we need this type of like interpretability. So by now it's really, as I already I think introduced here, is that we want to verify our predictions and make sure that these are actually correct. We want to kind of observe if things go as desired, if there's any flaws or biases that the model might have picked up. If the solution implemented by the model actually is the one that we expected, or if the model maybe finds a different solution to a problem. I think we heard about this in game solving, like in AlphaGo, for example, that the memory capabilities of these models are just so much better than any human capability that it kind of can exploit different strategies. So that's, I think, of interest. And also, more and more, it becomes a necessity to comply to kind of legislation and kind of requirements. For example, certain AI acts have been set in place by now. So, and these often require that you kind of disclose the underlying mechanism that a system uses to make a prediction. So with that, we can now go into what we actually want to do. So for now, we can say that we want to attribute somehow to our layer-wise representation. So a deep neural network has these kind of different processing stages. And at each of these steps, some computation is happening, and that kind of forms, for example, in image classification, increasingly high-level complex features. And now the question is, how can we go back to actually understand what happens along the way? So we want to kind of identify these relevance scores, RK, that tell us how important a certain neuron would be. And then once we know which are the important neurons, we can kind of go further and identify what these code for and when they strongly activate.
So can I just ask about, just I've never really thought about this, the conceptual setup. So you want to assign a score to each neuron to see if it's doing something important in some way, you'll tell us. But then, like, if I wanted to make sense of the idea that more than one neuron is important, is it just that each of them individually is important? Or is there some way to say, like, a collection of neurons is important in some way that's not attributable, like, to each of them separately?
Yeah, it's an ideal question. Yeah, we'll go into this throughout the talk. Yeah, for now, we kind of just mirror basically what happens in the forward pass. So we kind of consider every neuron, but of course, these neurons kind of are entangled and kind of produce assemblies that code for like a certain concept and together, let's say. But yeah, like we're going for the lowest level now, and then we can see how we can make maybe more group-wise inferences from it. Exactly, and then yeah, we can ask these like more general questions, like how can we understand what actually happens? Does it help our understanding of the problem-solving abilities, and so on? Okay, so how can we do this? So I think a pretty early idea was that even happened before deep learning is to exploit gradient information to kind of get an idea of what the model is actually doing. So you can kind of like compute a simple gradient for like a, let's say like a very shallow model, and this might already be sufficient. For the like more deeper architectures, this poses some problems because yeah, you have kind of all these like layer-wise dependencies of your layers, and you can have kind of more complex, also higher order terms that do not vanish. So kind of just focusing on the first order might not be sufficient. So yeah, this kind of Taylor decomposition helps you to kind of get a grip of decomposing your complex model function and approximating it with like functions that you actually can compute. This is like one view, and that's the gradient view. And you can have like a second view that I'm going to go after this. So one observation that was made if you do this kind of naively and you just look at these kind of standard gradients is that they are often quite noisy. So if you have a really deep neural network and you compute gradients, you can end up with these like super noisy, uninterpretable heat maps. Whereas if you kind of do this in a more faithful way, you can end up with something that's actually useful and meaningful. There's evaluation approaches how you can distinguish between them two without having to look at them, because yeah, humans maybe are also not the most reliable predictors for this. But yeah, this kind of like effect is usually attributed to kind of this idea of like shattered gradients that you observe in deep neural networks. And also generally like you need to kind of select the root point, which might be difficult. And also you run into these problems of like adversarials, so that networks are kind of prone to these fitting to noise, and you can kind of pick them up also in your explanation, and then it becomes very difficult to distinguish between what's noise, what's signal, what's an adversary, and so on. So yeah, this is the gradient view. In a second view, you can kind of look at this as from a relevance perspective that I already, I think.
I have a question over here.
Yeah. No.
Hi. Yeah, for the previous slide, I was just curious, conceptually, how would you distinguish between some noisy result versus an AI model genuinely coming up with like an alien way of finding different features than a human brain would?
Yeah, you have to test. So basically, you need to like come up with evaluation approaches to test if these features that are highlighted here make a difference for the prediction of the model. So you kind of have these like occlusion approaches or perturbation approaches where you would kind of like iteratively remove the ones that are highlighted here and see if the model actually cares for this feature. And then you could try and see how faithful these heat maps are in comparison. We'll come back to this also in a second, but yeah, I think that's a good mental model for now. Yes, so we have this kind of like a second view, which is kind of this relevance view, where you really, instead of looking at the model from a global perspective, so just computing these kind of global gradients, you really go layer by layer and like decompose the whole network into kind of like successive layers and analyze each of these components in isolation. And what can help you there to kind of set some boundary conditions between what is happening in these layers is you can kind of exploit this idea of like relevance conservation. So it's loosely inspired by like physics, let's say, because like the idea is that like you want to predict the function score that you have at the output. So f of x, for example, is some class score, some logit, let's say. And if you want to attribute this score through the whole neural network until you reach the input, it should kind of not get lost along the way, or also no new like information should appear in like magnitude along the way. So you kind of want to ensure that like the sum of relevance that you observe at each of these like successive layers kind of is constant and sums up to the score that you're trying to redistribute. So this is kind of this constraint here. And yeah, then the idea is here that you always kind of pool all your relevancies that flow from like a later neuron K to some lower layer neuron J to get like all the incoming relevance of a certain neuron. So kind of you pool all the incoming information into J, and then this would be your total relevance of R J at this position here. So yeah, then you kind of need to define how this redistribution actually happens, and a general kind of rule is written down here. So it's usually some proportion independency of the activation score that you observe at AJ, and also the strength of the connection between a neuron J and K, which is given by the strength of the weight, WJK. Sometimes it makes sense to introduce some functions here to slightly change the value, or like the way the weight is kind of being represented. But usually it's kind of some proportion of this factor here. And then you want to normalize by all kind of incoming relevance so that you kind of keep conservation in place. So this is kind of the more relevance propagation view. And one nice thing that was shown is that you can actually like unify these two approaches, and you can kind of like use the idea of a relevance model and then connect basically these kind of redistribution rules with like a gradient perspective that we have up here. So it's kind of like a local gradient perspective that transfers then to like the whole global perspective. And yeah, this is quite neat because it's much easier to compute gradients and much easier to implement also. And also it's much faster because you can basically exploit all the modern kind of like torch implementations to just compute gradients here. So yeah, there's a nice kind of theoretical connection here. And in the future, I think in the future slides, we'll mostly focus on this kind of gradient perspective. Okay, any questions on this so far?
So I was just kind of wondering about these gradients. I guess you always mean at least in the top line, the way you wrote it, the gradient of the output with respect to the neurons in some layer. You don't mean with respect to the parameters.
No, exactly. No,
not directly.
Exactly. It's like always with respect to like the input or like your activation that you care about. But otherwise, it's very close to backpropagation in the way like you can use the implementations and so on. So the chain rules apply in the same way. So yeah. Okay. So that's it for feature attribution. So yeah, now we are going into this kind of like structured explainable AI, where kind of this idea of neurons in isolation is kind of revisited. So yeah, what we found, especially like throughout the last, let's say, 3 to 4 years, that like this kind of heat map view is kind of useful, but it's also kind of limited. So this is the case that we observed so far, so that you have kind of a succession of layers, H, T, so instead of L, it's T here for the layer, but that encodes your input X in an iterative way, and you then have some final readout function G that gives you some prediction score. So this is exactly the setup that we just considered. And then what you usually end up with is this kind of like heat map type attribution. So you get this kind of first order scores basically. And this is kind of quite useful for all feed-forward neural networks, MLPs, CNNs, transformers, state space models. So yeah, everything that kind of just has a standard forward pass that only sees the input X at the first layer can be kind of represented with these heat maps. But you can think of like other cases. So for example, you can have bilinear structure. It's often the case in like unsupervised settings where you have 2 inputs, X and X prime. And you have some kind of dot product structure between these branches. So here, the example is like a similarity model, let's say, where you have 2 of these networks here. One's encoding X, one's encoding X prime. And you kind of compute a dot product between them. So for example, it could also be cosine similarity. And then what we find, if we kind of do this gradient analysis, that actually the correct way of attributing to these features is like by an interaction. So you kind of really consider groups of neurons to be relevant instead of single neurons in isolation. So it's kind of a more detailed and more like precise way of describing what the relevant features actually are. And yeah, this is kind of can be applied for similarity models and kernel models, like also in like these like retrieval type systems. So basically anywhere where you have this kind of dot product structure, also in multiplicative fusion, ensemble models to explain variances and so on, you can kind of like exploit this. So this is kind of the second order view, and then you can go even further. And this becomes necessary when you have like a nested structure. So when your input is somehow more complexly encoded at each step of your neural network layer. So here you have in your specific layer, let's say h of t, it always depends both on your adjacency matrix. So this is like a graph formulation here. So it's described by an adjacency matrix that gives you the structure of your problem and some like initial state h of 0. But the structural information is encoded repeatedly at each step. So now if you want to compute the gradient with respect to your inputs, lambda and h0, you kind of get these like recurrent dependencies that then result in these kind of higher order attributions. And we find these are really useful to explain graph neural networks, so that's how we initially discovered them. But you can also view CNNs or transformers from like a graph perspective, and then you can kind of view them also as interacting features of like some higher order. So yeah, along this kind of line, you become like increasingly specific in the information that you are encoding about what features are actually useful. Okay, any questions on that so far? And we'll go into like examples of each of these and throughout the talk, but so that the rough idea became kind of clear, that would be nice. Okay, so yeah, like a first example here, we'll consider like a first order attribution example that we derived via conservation of relevance. And we are going to consider like these state space models, Mamba models, which are kind of the new transformers. I think it's like often how they're often sold. So the nice thing about them is transformers are limited because they scale quadratically with the sequence length. So this was always like a huge problem for kind of all types of scaling problems. So that's why the invention of Mamba that introduced kind of recurrency and thereby managing to scale linearly with the sequence length has been like a big deal in the community. And yeah, it's kind of like argued to kind of being able to solve problems that require long-range dependency. It also has like more efficient memory storage and selective copying. So it kind of addresses some of the basic concerns that transformers always struggled with, because they kind of have these like full attention metrics where you have to basically represent each token to each other token in some way. And this, of course, comes with like scaling limits. So Mamba has like this different approach where you kind of go through each sequence element recurrently. And like similar, I think the architecture is still somewhat similar to transformers because you have this kind of block structure. So you have these kind of computation blocks that are made off of like several computations. And then you kind of like just stack these blocks together, and then you kind of solve your standard like sequence modeling tasks. So the internal like dynamics of the state space models look something like this. So it's inspired by control theory. So you have this kind of dynamic information processing independence of these transition matrices A, B, and C. And you have like a two-steps space model and like a hidden state H and your input X that are being encoded. Yes, then you have like your transition matrix A, which is kind of like a structured selection matrix. So it tells you how much information from a hidden space should I keep. And this is like an n by n matrix, so it really can fully transform the space that your H lies in a linear way. BT and C of T are only n by 1 and 1 by n respectively. So they have like more like a filtering, like gating role in this in the system. And all in all, this seems to really help to bring down the complexity of the processing. Maybe one important thing that's not obvious here is that A, B, and C of T all are input dependent on X. So they're kind of similar to what self-attention does, is that the weights of your attention matrix is dependent on your current input X. And in a similar way, A, B, and C of T are not just constants, but they're actually weight matrices that get updated with your current state X of T.
Okay, yeah. What is typical size of A?
A, so it's like a hidden space, so I think it's often something like hundreds of dimensions. So
100 by 100, 200 by 200.
yeah, like 768, I think, is like in the original paper, but I'm not entirely sure. But like around this scale. Yeah.
So not gigantic.
No, exactly. Anything else? Okay, so now one main problem with this architecture, again, is of course that we have no idea what actually happens internally. So while in their paper, kind of they do try to give some intuition on what these matrices are doing, but when you're actually trying to understand how a certain problem is solved, this is like a way to coarse level to just think of it as, okay, there's some filtering and there's some projection happening. So yeah, again, we kind of developed this interpretability approach to gain some more insight. And yeah, this is like the usual recipe that we follow. So we kind of like look at this block as a box that has some inputs and outputs. And these like red arrows here are our relevance that we attribute to these kind of vectors or like variables. And then when we kind of compute a naive gradient times input of this block, we end up with like a term like this that we then need to resolve. But first we can check if conservation is fulfilled by this kind of terms already, and we see that there's basically no correlation. So you want, again, conservation, the output score should kind of correspond to the sum of relevance at your input, let's say. This is like the blue line, if it would be perfectly conservative, but we see that there's basically no correlation if you do it in this direct way. And that's, of course, like a bit unfortunate, because the resulting explanations will be of this kind of noisy type that are pretty meaningless. So yeah, we had some experience from like analyzing transformers. So we kind of did a similar approach for Mamba models. So we kind of wrote down like a version of kind of the state space dynamics and like simplified a bit how these matrices are actually represented. So we kind of like introduced this theta t to combine these because they all depend on x of t, as I already mentioned. Then yeah, if you kind of compute kind of this term explicitly, independent of this diagram, you end up with the following equation for the gradients, for the gradient times input formulation. And again, now we need to check if like the sum of these scores is the same as the sum of these scores. So if the input sum of relevance is the same as the output at the relevance. And you can tell that this is not really the case because we have this huge term epsilon here. Of course, epsilon might be 0, but I think it's pretty unlikely because I think if you look at the specific term, so the function value f, the gradient with respect to the parameters is likely not to be 0. So also this is not likely to be 0. The gradient of the parameters with respect to your input, there's also not really a good reason why they should be 0 in general. And of course, your inputs are also not 0. Your state space representations, your hidden spaces are also not 0. So usually this whole term will not be 0. So yeah, it's like there seems to not to be like an easy solution here, other than basically viewing your kind of transition matrices as constants. So you can still, of course, update your matrices at each kind of step t with your current x of t. So you update them, but then for the gradient computation, you can view them as like a constant. So then this becomes a simple like linear computation, and you have no problems with any more complicated higher order gradients that would arise here. So it's similar to how you could also derive explanations for transformers, where you kind of your self-attention metrics would be like this, for example, here, b of t at x of t. But b of t also, again, depends on the input x of t. And by viewing this one as a constant, you just view it as like a weight matrix that tells you how much attention should I put on which kind of dimension of your x of t. So I think there is like some intuition that this might make sense. So you basically just assume that your parameters are given by the network instead of viewing them as self-dependent at each step. And yeah, we can show that this actually works. So conservation is kind of like restored. The remaining tilt that you see here is due to like bias terms that you usually have inside of your network. So you have usually like a plus b term in each of these layers. And these kind of make it like impossible to get perfect conservation, but they simply kind of shift your heat map, basically. So they don't really change the structure of your heat map, but they just kind of scale the values up and down a bit. So it's not really a problem for the analysis of them. Okay, so that's what we can do with like first order Mamba explanations. Far so good? Yeah.
Can you repeat again what's being conserved here?
The relevance. So it's kind of like the output. Okay, so the output is aimed to be conserved. So that's the score that you get out of the network for a certain prediction, and you want the sum of your relevancies to match this prediction score, so that you basically just redistribute through your network. But yeah, relevance should not kind of appear or disappear throughout this process. Okay, so with that we can like look at some use cases. Now before that we actually evaluate. So yeah, we come now to this like evaluation part that we already like briefly discussed. So how to check if this is actually like a meaningful attribution heat map is we can kind of like remove or add the most relevant ones to an empty sequence. So here we kind of start with an empty sequence and we add the most important ones. And then we kind of gradually observe how strongly the output probability in this case is being kind of produced. So kind of a faithful method should go up really steeply because kind of a few really important features should result in like a steep increase of the curve. So then we measure the area under this curve, and higher is then a better attribution method. Yeah, and if we do this for Mamba, we kind of see that like in comparison to like other more naive approaches, so most of them use kind of some gradient information, we kind of perform much better. And the same, yeah, is kind of like basically this reproduces kind of our findings that we already had for transformers, that you need to really like consider a faithful attribution method to get good results when you want to understand what features are important in these type of like complex models, because a naive kind of attention method would give you like a much less faithful result in this. But there's still like some positive scores here, so it's not terrible, but you can definitely do better than analyzing attention scores. Okay, this is the quantitative result. But now what can we do with these things? So for Mamba, since like there was this hypothesis that Mamba is really good at using long-range dependency information, we wanted to actually check this. So we kind of took like a data set of kind of longish input texts up to like 8,000 context window size. We computed these explanations, and then we basically looked at them. So first, like one example here. So we had this like long paragraph. So this is kind of skipping most of the lines. It's only showing the lines that contain some token that's considered to be relevant. And yeah, we asked the model so it's like an instruction model, so it can basically solve different tasks. And we asked basically for a summary of this whole paragraph. So in order to check if it's able to use information that was kind of presented to it at the very beginning in contrast to more towards the end. So yeah, the summary is kind of something like the album was released in April 19 something something, and like it predicts like the 72 as the next token. And we find that yeah, the model does attribute to some kind of occurrences of 1972 in the paragraph, just like as a rough idea. So it seems to match roughly what the model is doing, what it kind of highlights in the paragraph. But to kind of get more insight, we kind of did this over like a few hundred samples, and here show the distance of the relevant token to the generated one. So basically, how far did we go back into our context window to predict a certain token? So here, this would be close to the input. So this would mean you only use information that you find kind of towards the end, whereas these type of ones are the more long-range ones. So where you really have to kind of like memorize something that was presented to you a few thousand elements previously. So yeah, generally we find that there is kind of a tendency of these models to attend more towards the end of the whole paragraph. So I wouldn't say it's kind of like completely kind of like unbiased in respect to when the information was presented, but it's able to retrieve information from like earlier input stages. So it seems to be capable of doing it, but it's not like its default strategy. So I think there's a bias of these language models to produce and like use information that was presented closer towards the end of your input. If this is useful, I don't know. We find similar effects for transformers actually. they are even more so, I think, inclined to use these kind of like more later information bits. But yeah, this is basically just a tool that allows you to analyze this in more detail, and I think more kind of like, yeah, structured investigations are needed. But yeah, so this is what we did for long-range dependency. And we also did like a related study on multiple instance learning. So HPV infection is kind of a cause for head and neck carcinoma. And to model these type of things, so you have these kind of really complex histopathology data sets that you cannot process in like one forward pass. So you really have to like basically patch all of these things because you need a high resolution and then figure out like a learning model. And kind of multiple instance learning is kind of a framework to do this. So you kind of model these back of patches and then make a prediction if it's cancer or not. And this is kind of difficult to do because there's a lot of ambiguity. So maybe one patch has some like signs of some cancer cell, but all neighboring ones don't. So it's a bit unclear sometimes. Even for expert, this is like an extremely challenging task, and that's why people started using these type of models or like foundation models to kind of process the features of the patches, and then you need to learn some kind of like readout function. And the most common readout function that you use nowadays is something like a transformer or a Mamba model. And again, this is like important because if you kind of build some insight simply by looking at attention scores, you kind of see that basically everything is kind of important, so everything is kind of considered red. But we kind of know that these glands here that are kind of zoomed in here, they should be irrelevant for predicting cancer in this scenario here. But it becomes extremely difficult to actually like distinguish the irrelevant from relevant ones because kind of everything is considered like important because everything has high attention scores. And yeah, kind of with like these approaches that I just talked about, we can get kind of a more plausible picture that's also more in line with what experts actually think, so that the reason why this is like a positive case is like this region here, where you actually see a cluster of cancer cells, whereas kind of these glands here, they are kind of all considered less relevant or irrelevant and actually contribute negatively to the prediction of a cancer. So it's kind of more in line with like the predictions of the experts. But yeah, so this is kind of useful to get scientific insight. And yeah, we're looking forward to see what more the experts can tell us about it. Okay, so this kind of, I think, concludes the first order part. I think the summary, yeah, basically the main take-homes are you need to really carefully consider the structure of the model. So naive approaches can really kind of give you misleading heat maps. And yeah, you kind of need to think about how to distribute the relevance information throughout your network such that you get accurate results. Okay, but this is if you're interested in heat maps. Now we can look into like what second order attribution can allow you. So again, the prototypical case that we're considering here is this kind of like dot product case that then results in these kind of like second order gradients. So if we kind of have these models, so we have like one encoding model here, so it could be any deep neural network or like also like not deep, but nonlinear model. Otherwise, I think you can read out the coefficients without doing any of this. So this is basically the function you're trying to understand. And again, we're kind of following this idea of computing like a decomposition of this. So we expand the function into its terms. And now the question is, how many of these can we get rid of? So if you make some kind of assumptions on the functions that you're considering, so if you kind of assume you have like a linear ReLU type of networks and positively homogeneous functions in general, and choose your root point appropriately, you can actually simplify this whole thing to like to second order terms. And then this would give you something like a Hessian times product way of attributing. So I prime is now basically this thing. So it kind of gives you for each of your inputs, x and x prime, how important a pair of pixels or features would be. So it's kind of a scoring of all possible combinations between the features. And basically this Hessian times product formulation allows you to compute them in a direct way. But again, we have this kind of problem that we already discussed of like these like, unstable gradients and the whole root point selection problem. So again, we can kind of like robustify this procedure and come up with like a more faithful explanation method that looks something like this. So again, we kind of back to this like decomposition and like viewpoint, so kind of this more relevance viewpoint. So we can kind of formulate these type of different rules in like a relevance view, but then we can still implement them with like and unify them with the gradient view to kind of make them efficient to compute. What this also gives us like a more interpretable way of understanding how actually a certain high similarity score in our setting here is actually emerging. So you can analyze this function and observe that the activations of the neurons that we are interested in, so J and J prime, they need to be jointly activated. So both of these need to be like non-zero to produce like a positive relevance score RJJ prime. Also, like this whole term here needs to be positive, so they need to like jointly react. So the weights need to be such that this whole term is kind of positive, or can also be negative, of course. And also these pairs that we're considering, so RK, K prime, needs to have some relevancy as well. So if this is 0, of course, you can have any scores here. It doesn't matter. So you need to kind of have a specific setup in order to get like a positive attribution on pairs of features. And that's what I meant when I say this is like a much more selective view of information processing in neural networks, because you need to fulfill many more conditions here for this to be like a positive value, so to be relevant. Yes, so again, the question is how do we evaluate this? So we kind of came up with this toy scenario because there's very little ground truth data set where you actually ever know what the relevant interactions are. So if you have any kind of similarity data set, you know maybe what the ground truth score should be, but you usually never have any ground truth information on the pairs of features that are important. So we kind of came up with this kind of like sequence matching task where the ground truth is available. So as soon as you have like a same digit match, you kind of increase the similarity score by 1. You can train like a small neural network to solve this kind of very simple reasoning task. And then you can see if the different explanation methods can actually retrieve this picture. This is a kind of the benchmark. So also like here, this naive gradient benchmark that we have here. And yeah, you can see, I'll make the story short, is that kind of this approach that we propose is kind of like the only one that actually gives you something that matches closely to the ground truth. If you do, again, these kind of like gradient computations in a naive way, you kind of, again, have a lot of noise in your interactions. So again, it's a bit difficult to build any insights on these things. So yeah, I think the take home is, again, you need to do this carefully. And what can we do with this? So I think it's quite useful because generally you can kind of analyze unsupervised settings. Because in the previous way, setting, in the previous block of the first order cases, we had this kind of classification setting. So you always need to have like a clear task that you're interested in, like a classification task, for example. But what this allows you now is to basically extract representations from any model and kind of compare it to any other data point that you're interested in. So you can have like a reference data point, you can compare it to itself, you can compare it to a different modality. So it kind of gives you a lot of flexibility to kind of compute these type of attribution maps. So we did this for vision, and you kind of see these type of attributions that give you some insight into if the model kind of is presented with like images of like 2 birds, let's say, what does it actually focus on when it does like a comparison if they are like similar instances of the same class. We see that, as I think already often reported, is that models are highly overconfident in like these like eye features. We see also like undesired strategies. So here we have a horse and like a sheep, and they are considered highly relevant, but for like a wrong reason. So for the model, this kind of looks like the same feature, but it's the mouth of like a sheep versus the one of a horse. So it's kind of not sure if it makes sense. And here we have like a more philosophical example where it's not so clear what the similarity actually should be. So the model focuses more on the similarity between the 2 white instances of a cow, or a bull, I think it is, but kind of ignoring the brown one. So the model clearly kind of has distinct representations for like a white instance versus like another, like a cow that's colored in a different way. If this is what we expect, I don't know, but it's kind of maybe not to be expected necessarily if you just kind of like do like an image ranking and take the most similar example. And we did like similar things also for NLP here now on a corpus level analysis. So we kind of wanted to see if we kind of put these type of like a large data set of sentence pairs through like a GPT model. What type of features the model actually picks up on. So here we have kind of these different like post tags. So it can be like adverbs, adpositions, numericals, verbs, nouns, like all of the different types of words that can come up. And we find that like many of these like foundation models pick up on very simple relationships. So the most important interactions happen actually between nouns and nouns, verbs and verbs. And many of the more fine-grained structure that you would expect is kind of not so relevant. So I think our current models are kind of oversimplifying these type of tasks. So if you're basically giving the model an example of a sentence and ask it to, okay, find me like a similar resource, it might mostly do like token matching or like noun token matching. So not sure if this is like a stable strategy, but again, it allows you to kind of gain some more insight.
So, thank you. Is there a comparison of the scale of the model and the structure of the latent space that it can capture?
If we can compute it or if we can make sense out of it?
If there's work that either you or others have done that compare the two. So for instance, as you scale the model, do you get hierarchy better? Or what kind of relational structures can't you get in a smaller one, but you can get in a larger one?
Yeah,
So
I wouldn't know of any. Like I think it would be super interesting, but I don't know. I think this is kind of newish tools, and I think mostly people have looked at how important a certain like layer was, but not really at the relationships, I would say. So this was kind of like 30-layer like vision model, and this is kind of, I think, 12-layer GPT-like model. So as long as you can compute gradients, you're kind of good to go. So I think that's why these type of methods scale kind of favorably, because yeah, if you can train it, you can usually also get some explanation scores.
also, do you find that Mamba is better at hierarchical latent state structures?
I don't know yet. Like it's a good question, but I think that's really missing so far. I think like so far people mostly report that kind of it trains more stably and like it's kind of like more efficient in its training, but the amount of resources that have gone into like training transformers versus Mamba models is also not really comparable at this like moment in time. So I'm not sure yet. Okay, so I think yeah, this concludes already like the second part. So yeah, we can use this kind of like second-order attribution methods to understand better like how, in a very fine-grained way, features interact. And it kind of can give you some insights into these unsupervised settings that kind of make the analysis, in a sense, task independent, which is, I think, quite nice and powerful for the analysis of foundation models. Okay, and now like the third and last part also is like focus on the higher order explanations. So I think I already teased that we're going to consider graphs mostly. So graph neural networks kind of have the specific structure that they require you or like the data that you have like to define what type of nodes can exchange messages among one another. So you kind of like have these like adjacency matrix lambda, and you kind of feed it in at different steps of the graph neural network to kind of make sure that the structure is actually maintained and respected. So you do this kind of in two steps usually. So you have an aggregate function that computes new intermediate states z of t. So this kind of embeds your current hidden state onto the structure of the model. And then you use kind of this updated representation to get your completely new node representation, so h of t. And here you have some combined function that tells you how the incoming information from the neighboring neurons have to be merged. So you can just, for example, do like a mean pooling here, but you can, of course, do more like sophisticated approaches like a small neural network or something like that. But yeah, the important thing is that like lambda is repeatedly encoded together with the features. So if you then want to compute the gradients, you kind of get these walk type representations. So if you go like from the output, you go one step back, you kind of get attributions on nodes. So this would be first order. So they just tell you, it just tells you how important a certain node is at this point in time. If you then propagate one step further, you kind of start building your walk. So you get these kind of like second order interaction type things. So if two neurons are jointly important, you get kind of this like positive connection here. And if you go further towards the input, then you kind of can get longer walks. So a walk is then described by a succession of nodes, and all of them need to be kind of relevant in order for the whole walk to be relevant. So yeah, this can give you quite detailed insight into how information is actually processed along the layers in your model. And yeah, as I said, kind of when you compute the gradient for this whole thing, you get these kind of higher order terms. You can kind of change the structure a bit so that you only need to compute like local first order gradients in your connection weights. So this kind of simplifies the whole thing a bit. But yeah, that's some technical detail here. But yeah, in theory, you could kind of get the relevance of this walk by just computing like a third order gradient. But you can also get it by computing the local first order gradient and kind of combining them. It's still computationally kind of expensive to do it, but yeah, there's like follow-up work that can make this a lot faster. So what can we do with this? Again, the same story as before. So the naive result that we get here that just relies on the gradient is, again, noisy. So we can do this in a more robust way. And we can also do this in a faster way. So basically, this kind of like, when you combine these type of approaches with like efficient search algorithms and efficient masking algorithms that are kind of rooted in like a Markov assumption of how the features depend across the layers, you can kind of speed this whole procedure up by quite a bit. And yeah, what can we do with these type of things? So first we can evaluate again. I kind of go quickly through this. So we can see, so it's a similar idea. We kind of like remove or add the most important features, and we want to get kind of like high scores here. So here we get kind of high scores. There's not so many comparison methods that actually consider these type of higher order information. So at the point of when the paper came out, it was the only one actually, and all of the other methods are only first order approximations of this. So it's kind of a completely different level of complexity that we're comparing here, but it seems to be like beneficial to have all this additional information. These were all kind of like more simple synthetic data sets, and here we did it in all more like vision and NLP data sets. And you can kind of add nodes, but you can also remove them, but yeah, the picture kind of is the same. So you can always check if like adding the most important features gives you a faithful explanation, but also if you want to remove the least relevant ones, it shouldn't really change the output much. So it's kind of two different perspectives on the same evaluation, but they kind of give you complementary insights. Okay, so this is useful because you can now actually really try to understand better how information is being processed in your models. So here we kind of analyze something that we termed like relevance flow. So here, maybe as a first step, we view CNN as a fully connected graph neural network. And then we computed these type of interaction scores that we here show as a flow field. So again, previous approaches kind of would have attributed to just the nodes that correspond to some patch in your image. If you do this kind of naive approach, you kind of do get this kind of like flow fields, but they are somewhat noisy. And if you then kind of use like a more robustified version of it, you kind of get these like more stable, smooth relevance flow fields. You can kind of analyze them in a bit more detail. So we did this like for different blocks in the network. And I think in line with like the expectations, you kind of, for earlier layers, you get kind of flow fields that mostly trace the boundaries of your object. And the further you go through your network, the representations become more high level. So this means that your flow fields go towards specific compartments or components of your object. So here this would be the lid or the handle. And then in the later layer, kind of you have like a even more coarse-grained representation of the object. Yeah, so this is kind of useful to understand better how the information actually is assembled throughout the network. You can also use this to find kind of like surprising strategies. So one common known defect of like vision models is this kind of like joint dumbbell arm concept that many models learn. So if you present like a dumbbell without the arm, often models have like difficulties detecting it, because usually all the images in the training data set are kind of like this. So you always have someone holding a dumbbell. So models learn this kind of like shortcut. And you can actually see where this happens. So in like earlier blocks, these two concepts are still separated. So here you have like a separate flow field for the dumbbell, and here as well, and one for the arm, or like more like the wrist maybe. And then in the latest step, so in block 5, you kind of see how they merge into one coherent object. So if you would want to kind of mitigate this behavior, you would have to like intervene at kind of this step here. So yeah, it's kind of useful to really understand better how the information is assembled. So yeah, you can also like analyze NLP settings for this. So you kind of get these type of like graph structures. So you have like these semantic trees that you can analyze. We did here like this for movie reviews. So you kind of have a sentence like, first, I didn't like the boring pictures, but it is certainly one of the best movies I have ever seen. So it's a complex or like interesting example because the first sentence is like negative and the second part is positive. And if you do like a first order view on it, you kind of get, okay, the model thinks like is good. It doesn't really get it didn't like as a whole group like is negative. So it kind of has difficulties actually resolving the complexities of language. But if you do these kind of more advanced, like higher order techniques, you kind of see how the tokens interact and actually turn the whole first part of the sentence negative, whereas the whole like second part becomes positively relevant for a positive prediction. So it's kind of able to really capture the more complex structure that you have in language. And you can use this for all types of different problems that have like a certain like graphed structure. So in the paper, you can also find some examples on like chemistry, where you kind of predict the dipole moments of paracetamol. So yeah, chemists are currently looking into how we can actually use these type of insights to gain some ideas into how to build better molecules and how to also build better models. Okay, so I think with that, we are closing the third part. So again, this like specific structure where the input is repeatedly encoded results in this like higher order attribution explanations. Kind of need to slightly adapt the evaluation, but I didn't go into that. And yeah, these resulting walks offer you a more detailed and faithful view on the internal processing. And yeah, one of the things that I just wanted to kind of mention towards the end that I think interesting also to discuss with all of you is like, so in the age of foundation models, this whole idea of like a task is kind of distinct. So we kind of have models that can solve all types of tasks. So they classify, they generate, they can maybe reason in abstract ways, they can compute similarities, find you similar samples. So the question of what is a relevant feature is kind of maybe a strange question that like used to be our like common framework. Especially since you can ask these like open questions, like, I don't know, what is a person? And the model will give you some answer to it, but the relevant information will not be in the input. So you need to find ways to actually gain insight into what happens inside the model. So I think our work here kind of contributes to this by resolving more complex structure in the model. And kind of goes towards kind of really finding these more functional computations. For example, also circuits, I think, are like a common way of looking at these functional components nowadays. But it's kind of open how we can formalize these type of like the discovery of these mechanisms. And I think some of these approaches that we developed could be quite useful for this. I think a more general question is also like, do we need to induce more structure? So we have seen that like inducing structure changes the way the model solves certain or resolves certain features. We've seen like and discussed many of these like grokking, memorization versus generalization problems. what came to mind here was maybe we should just separate memorization and generalization in the models. Maybe we just need like a memorization module that's separate, and we kind of can, in a completely interpretable way, distinguish when the model is doing which. Because also like some of these models learn like maybe reasonable circuits. So we have an example here from last year at NeurIPS. So in order to implement a greater than operation, this is kind of a circuit that these authors found. It seems pretty complex to me somehow. Like this is usually like one attention head, and these are different layers. So to kind of implement such a simple function, I think the compositionality benefits that one could hope for are not really exploited here. So I think there's some work to do to improve these models. And yeah, and I think with that I would close. So yeah, thanks for listening. And yeah, if you have any questions.